Hello everyone, thank you for choosing to view our ASRU 2023 poster presentation video on reducing the cost of spoof detection labeling using mixed strategy active learning and pre-trained models. My name is Mark Lindsay and I will be presenting the work that I did in collaboration with Nathaniel Robinson, Francis Kubala, and Richard Stern. In this presentation, I will begin by covering the problems being addressed, including spoof detection and active learning. Then I will explain the details of our contributions, introduce the experiments that were used to test the methods we developed, and discuss the results of these experiments. So let's start with motivating the problem. Spoof detection is mostly necessitated by privacy and security, specifically pertaining to information, services, devices, and other assets secured by automatic speaker verification technology. It also has potential to detect scam phone calls or pernicious deepfake audio, as both are becoming increasingly common. One major roadblock for developing spoof detection algorithms is the lack of related data. Individuals and organizations, including machine learning challenges such as ASV Spoof, which has been in existence since 2015, struggle to generate and label large amounts of spoofed and bona fide audio data. This is where active learning comes in. Since the primary goal of active learning is to train a machine learning model to perform its intended task well using a limited amount of data, it is very well suited for addressing the problem that spoof detection faces. In fact, active learning has been used this way at least a few times in the past. Active learning is, however, still a work in progress, despite being a major machine learning research topic since the 70s. One deficiency of active learning methods that our work addresses specifically is the fact that these methods only use one single unchanging strategy to determine which samples should be queried. This is a design flaw that contributes to the issue of query selection criteria becoming less and less meaningful as the model is exposed to more data. This can be seen clearly in the figure, as the average value of the softmax sampling strategy criterion for all potential training samples approaches the maximum after just 500 samples have been added to the training pool. So what we show in this presentation is, first, how we apply active learning to spoof detection, including experiments we performed to identify which pre-trained speech models are best for this task, and second, a new method of active learning that uses more than one query selection strategy during training. We call this mixed strategy active learning, or MSAL. And just to give you a sneak peek, we show that MSAL can significantly decrease error compared to a fully supervised model and do so using less than 10% of the training data. Now let's get into some of the technical details. In our approach to active learning, which follows the active learning for non-semantic speech tasks, or ALLO algorithm, a single active learning step consists of feature extraction, classifier training, and query selection and labeling. This process is repeated until the model has achieved desirable accuracy. As I mentioned earlier, traditional active learning methods only use a single query selection strategy. Some common strategies, and the ones we use in this work, include random sampling, softmax-based strategies, and negative energy. Here, softmax-based strategies can be understood as entropy, least confidence, or margin-based strategies, since all of these strategies will pick the same samples for a binary task like spoof detection. Negative energy is an energy metric calculated from the logits before the softmax operation is applied. This makes it less susceptible to the plateau issue that the softmax-based methods experience. As shown in the figure, the only difference between traditional active learning and MSAL is the fact that MSAL can select the optimal strategy from a pool of strategy options for every active learning step. The neural network architecture we use for the spoof detector in this work is a contrastive classifier architecture. The first half of the network acts as a contrastive Siamese network that separates the two classes and clusters them as tightly as possible to minimize the contrastive loss function. The second half of the network acts as the classifier with the objective of minimizing classification error. The two losses are combined linearly with weighting parameter lambda before backprop. Using this active learning algorithm and network architecture, we performed a few experiments. These experiments consist of one to determine which pre-trained embedding network functions the best as a spoof detection feature extractor, and one to show that MSAL can outperform the fully supervised baseline model and the other active learning methods. The data we used for these experiments is the ASV Spoof 2019 data. We use all the same data splits and evaluation metrics as were used in the challenge. We tested 5 different pre-trained embedding networks as feature extractors: WaveLM, Wave2Vec2, Hubert, XVectors, and eKappa TDNN. Along with the different feature extractors, we also tested different values of the loss weighting parameter lambda. Remember that if lambda is 0, only the contrastive loss is backpropagated. If it is 1, only the classification loss is backpropagated, and anywhere between 0 and 1 combines the two losses. For the second experiment, we tested 3 MSAL methods in addition to the individual query selection strategies listed before. First was voting, where the samples were ranked by each individual strategy, and the samples with the best average ranks across the strategies were chosen. Second was the plateau method, where the softmax method was used as the default method while the average maximum value is less than 0.99. For any active learning step where the average is above this threshold, the algorithm reverts to negative energy. Third was using an SVM to predict which method would be best at any given active learning step. The SVM was trained on information from previous runs, like the rank of the individual strategies according to error rate. As you can see from the figure, the rank seems to behave quite erratically, making it difficult to predict. Now here are the results of our experiments. The clear winner of the 5 feature extractors was WaveLM, which performed very well with both the combined losses and only the classification loss. Hubert also performed very well. It is notable that only these 2 feature extractors benefited from combining the loss functions. The others performed better with only cross-entropy loss. Since the combination of WaveLM and lambda equals 0.5 performed the best, this setup was used for the active learning experiments. And here are the results of those active learning experiments. Note that the results show the mean and standard deviation of the evaluation metrics over 5 trials. The best single strategy active learning methods were negative energy and softmax, both of which outperformed the fully supervised baseline with similar scores. The best overall method, however, was the plateau method, which performed better than all baselines and other MSAL methods. In fact, the plateau method was the only one to outperform the fully supervised baseline with statistical significance in terms of both EER and TDCF over the 5 trials. Some of the other active learning methods came close, but the p-values were just above 0.05. In conclusion, we were able to show experimentally exactly how much more efficient training spoof detectors with active learning can be. Performance can improve significantly while using less than 10% of the volume of training data. We are very grateful to Probity for providing funding for this research. The authors would also like to thank Roshan Sharma and Jiwan Jung for their feedback and advice on the project. Thank you for listening to our presentation. Here are a couple of references.